So please welcome to the first presentation of this afternoon to Aline, that will talk about some geomechanical models. Thank you.
Thank you. Hello, everyone. So I'm going to present the challenges we faced on our work on two study cases related to comparison of displacement measure by InSAR and simulated by geomechanical model and hydrogeological model coupled together. So first, I'm working in the framework of the LASUGEO project. So the aim of this project is to map and quantify the impact of groundwater withdrawal on the surface of Belgium using long time series of different geodetic techniques. Me and my colleague Atifi, who is also here at this conference, we are working on two different cases. The first one is Antwerp and the second one is Leuven. I will present a little bit them later on. And so we choose these two study cases because we observe, well, we identify some deformation in this area using the radar imagery and observe using PS-InSAR technique. And the hypothesis made on this area is that due to groundwater withdrawal, there's the delayed subsidence occurring in low permeability layer. So our methodology was to create a local or and regional 3D groundwater model and couple them with 1D geomechanical model using the SUMP package. In the case of groundwater withdrawal, this methodology is the most commonly found in literature. So first thing, to monitor, to identify deformation, there's a few methods that existing, like extensometer, LiDAR, GNSS, which are more on the local scale. And in our case, we used InSAR method to identify, as I said, the deformation. The advantages of InSAR, it's cost-effective, it covers a larger area, and it's also having a high precision. But the disadvantage of this method is that it's limited temporarily, limited accessibility because some of the satellites are private. And since the technique of work doing on the images is sensitive to different type of area. And as you can see in the right, it's an image of the Leuven area, which from the Envisat satellite and covering the period between 2003 and 2010. And it's been, the one you're seeing has been it's been worked using the PS-InSAR technique because it's the best technique for urban area. So after that, what is the cause of the land surface deformation? So the existing natural and anthropogenic processes that can cause deformation. So excessive groundwater withdrawal, compaction of unconsolidated sediments, excessive injection of wastewater in aquifer, decomposition of organic soil as in boulders, and mining or oil and gas extraction. And as I said, in our case, we are working with groundwater withdrawal. So to model the impact of this exploitation, we are basing our theory on the Terzaghi's principle, which is that the total stress is equal to the effective stress plus pressure. So when we are pumping water, there's a decrease in the water pressure in the saturated geological medium, which induce actually an increase in the effective stress in any condition. So there's different way to model, numerically model all these hypotheses. The three first one, the black box model, Akitar drainage model, and pore elasticity model, are usually used as a predictive model. The black box model is the easiest to implement compared to Akitar and the Akitar drainage model and pore elasticity model, which are process-based models, so they need hydrogeological, geomechanical, and physical properties of the area of interest. And finally, the most recent one are artificial intelligence methods, which are usually used to determine the likelihood of subsidence that's occurring at a given location and to take into account the different cause and the actual subsidence that's occurring at the same location. So most of the model, the actual model are basing their theory on these two different models. And in our case, we are using the Terzaghi principle, as I said before. So we are in the archital drainage model, and there's existing some numerical tool. The first one is Compact that was developed in 1975. It's a finite difference model that's used to express the cumulative 1D compaction in the Akitar. Later on, the IBS1 was developed by USGS in 1990, and it's doing the same as the Compact and adding the modeling of subsidence in semi-Akitar layer. And finally, in 2002, the sub-package was released, which is taking into account what IBS1 was doing and adding also the delay subsidence that can occur during deformation. So now I'm speaking about the two study cases that we study. First, there is Antwerp. So that you know, Antwerp, the whole area of Antwerp is suffering subsidence. There is two hypotheses to explain this subsidence. First, due to embankment, there is a compaction of the shallow layer. And the second hypothesis is that the exploitation of groundwater in deep layer create compaction in the deep low permeability layer. So to exclude the first hypothesis, the local model was created, but outside of the shallow layer. So we only take into account the hypothesis of compaction in deep layer. And this model was created here because, as you can see in A, B, and C, there's subsidence occurring in this InSAR measurement at the free period of time. And finally, it was decided to do a local model in this area because there is really water drawdown visible here, which is observed in one of the deep aquifer. So as I said, for the methodology, in the case of Antwerp, the model was run through 2007 and 2016. The first thing was to do a hydrogeological model using hydrogeological parameters from literature and report. And as a solicitation, the piezometric level time series were used. After that, a geomechanical model was created using the sub-package, and the compression and swelling coefficient used by sub-package are coming from literature and report. By combining these two, we are getting the vertical deformation in each hydrogeological unit. So the idea is to compare to PS point in the same area of the local model. So the second column is showing cumulative displacement that we can see in InSAR. The third column is showing the displacement that was calculated by the sub-package, and the last column is a difference. And here you can see the RMSE between the PSI displacement time series and the cumulative displacement from the model. So now about the study case of Leuven. So as you can see here in A, B, and C, this is the InSAR measurement through 3 different satellites and therefore 3 different periods of time. There's deformation occurring and really visible here. And on the right, what you can see is the evolution through 30 years of the pumping that's occurring in the same area. And you can really see that there is big pumping occurring in the same area where you can see deformation in Leuven. That's why it was chosen as a study case. And so we are going to take interest in this part. So this is the result of my sub models using sub-package, and you can see with the orange line that in terms of trend, we have the same trend as the InSAR imagery was showing. We have like compaction during the whole 30 years. However, when you look at the absolute values for the sub-package and what we have in InSAR, it's really different. So, as I said, the trend comparison between InSAR and the result of the geomechanical model is good. However, for the absolute value, it's pretty complicated. So the different hypotheses to explain that are, first, about the uncertainty given by InSAR. So as a general uncertainty, we have the deformation pattern that cannot always be retrieved if the density of the PS point are insufficient. There is also challenges in monitoring very local deformation as we have due to low resolution of non-commercial data. And in our case specifically, we can only use the result of the InSAR because it's as a comparison, because it's only estimation, so it cannot validate our model. And also the InSAR measurement that we have, it's not continuous, so we cannot use it as a long time series to compare it to our result over 30 years. Other uncertainties are from the groundwater flow model. So we have missing solicitation. The result of our modeling show that clearly we don't have information about the pumping that was occurring at the beginning of the 90s and before. So it's really visible on the deformation that was occurring really in the north of Leuven. There's also missing observation. In the case of Leuven, I'm speaking about Leuven because it was my case. We only have 0.08 piezometer per kilometer square, and it was for the regional model, so it's really, really low. We have also oversimplification of the geology because of the type of model we're using. We express the geology as a layer cake, and we are using a unique set of hydrogeological parameters for conductivity, specific storage, specific yield that's implemented for each layer. So there's no special it's not differentiated spatially, but only in depth. And finally, as I said, we are using process-based models, so it takes high parameterization. Uncertainty for the geomechanical model is also high parameterization, and the sub-package we're using has a oversimplification. Because of the sub-package, it's actually using the compression and the swelling coefficient as a unique value for each layer. And these values are coming from boreholes that are usually not exactly at the same place we are looking at. So it's far and it's a lot of assumption. And finally, as I said before, it's complicated to compare the sub-package and the InSAR measurement because the overlap in time of the dataset is really difficult. So finally, what is this study showing? That the InSAR technique that we have right now provide valuable approach for accurately monitoring surface deformation. It's also showing that now we have a lot of methods to model the variation in groundwater level and compaction. However, the issue is the practical implementation. We have a multitude of factors that can influence each of these methods, and it creates a lot of uncertainties, which making it difficult to compare the results. So thank you very much for listening. We have 2 different posters about our cases that's been showing on the other level if you want more insight about our results. Thank you.
Thank you for the nice presentation. Any questions?
Thank you for your nice presentation. I was wondering, you have been focusing on the deep subsurface and the contribution of that to total subsidence. I was wondering, do you also have an estimate or idea of what will be the contribution of shallow subsidence? Unless all the uncertainties, of course, but...
Yeah, no, I can answer for Leuven. We are taking into account in the model, but when we doing the geomechanical calculation on the area, it's showing that most of the subsidence occurring will go into deep layer and not in the shallow one.
Yeah, but what do you mean with most? How can you give a percentage or something like that?
I'm recalling my calculation. Because it's so thin for the shallow layer, I think like you can say like 90, not 90, 85% of the subsidence is occurring.
Okay, thank you. Other questions?
Thank you for this nice presentation. You just mentioned that you missing the groundwater exploring data, right?
Yeah.
Yeah. So how do you deal with the problem when you do the modeling if you don't have this data?
In the case of the one I showed the result for the sub-package, we have really close piezometers, so it's giving data about the groundwater. In our case, the one that's farther in the north, we're using farther piezometers, so it's a lot of assumption, but not doing much more because we don't have the data and I'm not the one working on it.
So you actually do not do the groundwater flow modeling, right?
Yeah, I'm doing the groundwater flow modeling, but I mean, you're asking about the data issue.
The groundwater pumpage?
Yeah. Oh, you mean the missing one?
Yeah.
Yeah, well, it's data, it's all data that's been not recording. I already went through archives a lot to get a little bit more of the data, but we made a lot of assumption in the model to take care of that and change the boundary limit also to take that into account. But we've done, I think, the most of it.
Thank you.
I miss the geological model of your work, the conceptual model. Maybe a lot of uncertainties in the results can be resolved for the difference between the shallow and deep contribution. Are you working on that, or are you planning to work on that?
I'm sorry, can you?
The geological conceptual model. Yeah. I miss it. You are working on this?
The vertical model?
The geological conceptual model.
No, I'm not working on that.
And you are not intent to work on that neither.
I mean, right now it's not the focus on it.
Okay.
There's other issue we're working currently, but it can also be a good way to go after that to resolve some uncertainty.
Thank you very much for your presentation.
Thank you.